You will not have many notes with this. In fact, you may not have any. You may have blank pages. So, let's preface this section. There's a lot in it. There's not that many questions on it. So as we talk about this, I'll tell you what you need to know and what you don't need to know. And some of it I'm going to tell you need to know for your homework, but you don't need to know it for my test, and you don't need to know it for the AP test. Okay with what all I'm saying? So 12.3, inference for slopes. Inference for slopes. A lot of this is going to go back to chapter 4. So chapter 4 was bivariate data. That was the linear regression stuff, where you had a slope, you had a y-intercept, you had y hat, we had r squared, we had the standard deviation of the residuals, we had residuals, we had all kinds of things with that chapter. That chapter is pretty full. And so a lot of this is going to go back to that chapter. And so, truth be told, I use this as a review of chapter 4 more than I use it as 12.3. Okay? So, inference, which is making predictions from the population or to the population of slopes. And we know what slopes are. Okay? So, let's talk quickly, or not quickly, let's talk about this chapter. Maybe we won't. Yeah, maybe we will. Okay. So just look at this and kind of soak all this stuff up. And again, don't write much of this stuff down. Don't write much of this down. But we got a scatter plot. Y'all remember what scatter plots are? They're bivariate data. So I don't know what we're going to have on the X. We've got something on the Y. It says the duration and interval between the eruptions of Old Faithful. All 263 eruptions in a 63 month, in a single month. So that's the population. That's the population for that month. Just kind of picture this, right? We got populations, we got samples. The population least squares regression line is right here. That's all 263 points, and we can find the least squares regression line, the LSRL, for that particular data. You put all 263 points in, you find the least squares regression line, you'll find the slope, you'll find a y-intercept. Oh yeah, we kind of remember all that stuff. Y hat equals, because you're predicting a y value. Sometimes we predict it dead on, and sometimes we miss it, right? That's a positive residual, negative residual. Just again, kind of soak all that stuff up, stuff from previous chapters. Okay, so again, that's the population. That's the population. We'll picture this. I'm going to be taking a sample. So we're going to take a sample of, I don't know, 30 instead of 200 out of the 263. Well, we know if I take 30 of these dots, that line will not be exactly like that. That least squares regression line will not look exactly like that. So a regression calculated is a sample regression line. We know it's y hat is equal to a plus bx. Some of you put mx plus b still. That's okay. They don't care, but we just know we have a y-intercept and we have a slope. And we have a predicted value of y. Y hat is the estimated value, right? A is the sample mean, and B would be the sample slope. Again, that's what all we did in chapter 4. Don't worry about that. As long as you know it's y is equal to a plus bx or mx plus b or b plus ax or whatever you want to call it. Who cares? Something in front of an x and there's a variable by itself, right? Well, we have the population one. And so the population one, instead of y hat, let me turn this to a pencil. Instead of y hat equals a plus bx, they're going to turn it into mu sub y is equal to alpha plus beta x. Okay, so kind of see my notation with that. So this is what all we did in chapter 4. That's what all we did in chapter 4. Because everything was samples. I know you didn't notice it at the time, but everything was samples then. Well, now we're looking at populations. And so rather than saying y hat, we actually have mu sub y, okay? Mu sub y. And we have an alpha and we have a beta. Beta lines up with B, alpha lines up with A, mu sub y lines up with y hat. Just kind of, again, just take this in for what it's worth, okay? Populations always deal with Greek letters, right? Mu, P, X bar, sigma, all those are populations. X bar, P hat, S sub X, all that's samples. This is all samples, this is all populations, okay? Mu sub y is the mean for a given value of X, alpha is the population intercept, B is the population slope, right? So here I have scatter plots for, I took 15. I took a sample of 15 instead of a sample of 30. So here's 15 dots. The blue is the population line. That green, or whatever color you want to call that, is the slope of the least squares regression line from that sample. If I did it again, I have another green line from that sample. If I did it again, I'd have another green line from that sample. You can see that they're close to the blue, but they're not exactly the same as the blue. And we know that all from samples, right? Because of sampling variability. If I take a sample of something, I'm probably not going to get the same thing as the population, and I'm probably not going to get the same thing as the previous other samples. I'd be more surprised if they were the same. Y'all okay? But they should be close. It should be close, provided it's a good sample. So kind of just soak all this stuff up. Again, we have a y-intercept, we have a slope, we have a y-intercept, we have a slope, we have a y-intercept, a slope, and they're all a little bit different. Notice that the slopes of the regression line were 10, 12.5, and 15.7. Didn't notice that, but now notice it. Vary quite a bit from the actual slope of the population, which is 13.29. Some of them are a lot closer. That 12.5 is actually closer. The 10 is further. Sometimes we get closer, sometimes we get further. The pattern of the variation in the sample slope is described by its sampling distribution. So we got a little bit of these sample distributions, right? And if I did this over and over and over and over again, right now I have a distribution of samples, just 3. If I did it over and over and over and over and over again, I'd have a sampling distribution of all these slopes. Just again, kind of just soak all that stuff up. It's previous knowledge, but we're kind of just tying it together. This is a distribution of all those slopes. This is a distribution of 1,000 simulated 15. So this is not the sampling distribution. This is a distribution of samples, 1,000 of them, right? The blue is the true sample, and the greens were all those other samples that we took that came close to it. You'll probably see that 10 that was up here. That's really far away. What was the other one, like 12.8? Okay, you're kind of soaking all that stuff up, right? So we have a sampling distribution of slopes. Again, you don't need to know any of this stuff, okay? But if we choose an SRS from observations of X and Y's, so I'm going to choose a point from the population of all the points, then I would, so this is the population line, I would have a mean of a sampling distribution, which is also equal to the mean of the population. And now I would have a standard deviation of the population. And then, of course, the sampling distribution will be approximately normal. Again, all this stuff is not needed to know. It's not needed to know. But we already know this about sampling distributions. We know the mean of the population is equal to the mean of all those slopes. And we know that the standard deviation is typically equal to the square root of n divided by it. And we know that the sampling distribution is always normal, provided we have a large enough sample size. Again, you don't need to know any of that stuff for this chapter, but this is kind of tying in chapter 7 to it. So now picture this. This is somewhat of a three-dimensional type shape. This is the population slope. That's the population slope. Here is a population point, but then I have these normal distributions that are around each one of those points. You have to kind of picture this as three-dimensional shape. You have all these normal distributions that are around it. So I would expect to get somewhere within close to this, close to these, close to these. Bear with me on that. Here's the conditions for linear regression. and they are completely different than all the others. You will have questions on homework on this. You will not have questions on the test on this. You will not have questions on my test. I have never seen them on the AP test. Okay? But these are the conditions for linear regression. Well, the first thing is we got to assume that the data, or not assume, the data needs to look linear. If the data doesn't look linear, then of course we can't do a linear inference. So we want the actual relationship to be linear. How do we know it's linear? Well, the dots look like they fall in a line, right? The dots look like they fall in a line. Also, remember how we also tell if they're linear? We look at the residual plot. Oh, I don't remember that word. Maybe I kind of remember residual plot. We want the residual plot to be scattered. We don't want that residual plot to be scattered. If the residual plot's scattered, then the original set of data was a line. If it's not scattered, if it follows a curve pattern, then it wasn't linear, right? We need to adjust that. Again, all this stuff is from chapter 4. So we need to know that it's linear, okay? Need to know it's linear. That one looks linear. That looks like a line. That's a residual plot. That one's bad. Okay with that? So I cannot do inference for a linear regression for this one because it's not a line. Duh. Okay, it's not a line. It needs to look like a line. So good, scatter plot forms a linear shape. Bad, the residual plot has a curved pattern to it. Okay, every point needs to be somewhat independent of the previous point. Every point needs to be independent of the previous point. And we also need to check the 10% condition. Okay, so individual observations are independent, and we need to check the 10% condition. Again, these are just questions you're going to see on your homework tonight. You will not see them on my test. You will not. Independent. There's a reason why I'm giving to you in this order. Okay, so if the sampling's done without replacement, we need to check the 10%. We need to check independent. This is like one of those that I have never seen this one violated. I've never seen this one violated. Normal, okay? Any particular X value, the response, we want to follow a normal distribution. And here's what we mean by that, okay? Let me click on to the next one, okay? You want to make a box plot of the residuals. You want to make a box plot of the residuals. Now, again, for homework, you don't have to make it. It will be made for you. I've never seen this one violated. This is kind of like your one in means where you had to plot the box plot and show that the sample data looks somewhat approximately normal to be able to use it. Same thing here. I've never seen that violated. We have to use this one pretty loose. But again, we basically want those residuals, the residuals to follow some type of a normal pattern. The residuals. Okay. We want equal standard deviations about the line. Equal standard deviations about the line. Equal standard deviations about the line. Both of these are residual plots. This one looks pretty good. All these points are somewhat equidistant from the line. There's nothing really bad, really good. That one's bad. They start off with a small standard deviation and then they get to a fairly large standard deviation. Again, homework only. Homework only. None of this will be on your test. I've never seen it on the AP test. Equal standard deviations. This one's good. That one's bad. And I haven't seen anyone's bad on your homework. It's just, those are things that you have to recognize. And then random. We want to make sure the points are selected at random. We want to make sure the points are selected at random. The data comes from a random set. L-I-N-E-R. See it? Liner. All this stuff is dealing with lines. Those are conditions. It's the only one that has different conditions than all the others. But really, it's the only one you don't need to know for my test. And I don't think you need to know it for the AP test. And if you do, hopefully you can remember liner. Hit me.
So on your test, like, even if we're doing that, you don't have to.
No. No, every one of these that I've seen on AP, it always says the conditions have been met. Every one of them have said that the conditions have been met. And big secret, I guess, maybe not. I bet I've taught this lesson out of the 15 years 3 times.
Why are you teaching this?
Because we have time. We have time. On your test, there probably won't be 3 questions on this whole lesson. Okay, again, I'll emphasize that. All right, so here's what they're going to give. Just look at this. This is an example that came from the book. Could be something you can see on your homework. You will not see this on the test. Miss Barrett's class did a fun experiment using paper helicopters. After making 70 helicopters using the same templates, students randomly assigned 14 helicopters to each drop from heights. So there, yada, yada. There you go, good. Team of students released the 70 helicopters in random order, measured at flight times in seconds. The class used computer software to carry out the least squares regression line analysis for this data. Here's a scatter plot, residual plot, and histogram of the residuals. Check if the conditions have been met. So here's a scatter plot. Looks linear. The residuals all are somewhat equidistant from the line. There's a pattern of the residuals. So line, it looks like a line. I, each one's independent of the previous one. N, what was N? Normal. The residuals look normal. We want the equidistance from each other. And we got a random sample. Y'all okay? Again, very similar to a question you're going to see on your homework, but I promise you, you will not see anything like that on my test, and I don't think you'll see it on the AP test. So, good, good, good. Everything's good, okay? Don't overreact to minor issues of the graph, kind of like when you plotted the box plots. When you plotted the box plots, don't overreact to those thinking, that's a little skewed. Nah, it's got to be really obvious. Really obvious. Okay, this you somewhat need to know, but again, it's very, very common sense, I think. A, right, estimates alpha. A estimates the value of alpha. A is the y-intercept of the sample. Alpha is the y-intercept of the population. So A estimates alpha. S estimates sigma. You already knew that one. We already knew that S estimates sigma. B will estimate beta. So B is going to be your slope. A is going to be your y-intercept. Okay? You don't need to know this formula. You just somewhat need to know that S, the standard error sub B. That you need to somewhat know. Just a notation. S, E, sub B. This is the standard error of the slope. Standard error of the slope. Very few times are you actually given the standard error. Most of the time you're given the standard deviation. You have to find the standard error. Okay? Remember, it's like S over the square root of N. Or it's square root of P, 1 minus P over N. All of those are standard errors. Well, this is the standard error of the slope. But guys, they're actually going to give you that value. They're going to give you that value, so you don't need to use this formula. Okay? So notation would be the only thing you would need to know for my test, for the AP test, or for your homework. A estimates alpha, B estimates beta, and S estimates sigma, which that one you already knew. You do need to know that B is always going to be your slope. B is going to be your slope. A is going to be your y-intercept. We need to stick with y equals A plus BX. Y hat equals A plus BX. Okay? This formula you don't need to know, but you need to know what that stands for. The standard error of the slope. Okay, the standard error of the slope. This is common. You need to know this, but you already really kind of know this from chapter 4. I'm just reminding you of it. Earlier, Ms. Barrett's class used computer software to perform a least squares regression analysis of the helicopter data. Recall that the data came from dropping 70 paper helicopters from various helicopter heights in inches, measuring the flight times in seconds. Some output in this regression analysis shown below. We checked the conditions performing earlier. Again, that's what they're going to say. Assume the conditions have been met. Computerized printout. You got to know how to read a computerized printout. You got to know how to read a computerized printout. Okay, guys, please. So you always have a predictor. You always have a constant. You always have some variable. You always have a constant. Oh, I kind of remember this from chapter 4. You always have a constant. You always have a predictor. And you always have a variable underneath it. This one says drop height. So that is the X variable, is the drop height. Flight time versus drop height. Flight time must be the Y. Drop height must be the X. Okay, and how do I know that? Because this one says drop height. So whatever that one is always your X. Here's your constant. There's always a constant. There's always a constant, and there's always some variable below the constant. It might be above it, but most time it's below it. Okay? The constant, coef. Y'all remember coef? Yes? That's the coefficient of the variable. So this is the coefficient of a constant, which just means the y-intercept. That is the y-intercept. And then this is the coefficient of the drop height in centimeters, which is the coefficient of x, which basically means it has to be the slope. That has to be the slope because it's the coefficient in front of drop height. Okay? Here is S, if you guys remember that, that's the standard deviation of the residuals. That's not important today. Here's R squared. That was important in chapter 4. That's the R squared. That's the direction. No, that's the percent of variation in Y, described by the least squares regression line. Oh my gosh. You don't need to know that for this chapter, but you need to know that. And R squared adjusted, we don't ever use. R squared adjusted, we don't ever use for anything. Now, in chapter 4, I told you don't worry about this other stuff. We'll get to that later. Well, here we are. Here's the standard error of the coefficient. Standard error of the coefficient. That's the standard error of the intercept, which we won't deal with intercepts. We always deal with slopes. We deal with slopes. So this is that standard error of the slope. That's that SE sub B. Okay, that's that SE sub B. Here is the T critical value. That's the T critical value. These deal with T slopes or T distributions. So we have Z's, we have T's, we have chi-squareds. These go back to T's. And then that's the p-value. That's the p-value. That makes sense. If that T is 28, that p-value better be pretty darn small. Okay? So you need to know how to extract all that information from this. Their question is, what is the estimate for alpha? Interpret that interpret that value. All right, so alpha is always the y-intercept. Beta is always the slope. I don't know how you want to remember that, but alpha is the y-intercept, beta is the slope. So that estimate is negative 0.03761 for this particular question, okay? I should have put this on your notes, but again, we'll live and learn. Okay, now I want to estimate that. Well, y'all remember how we describe the slope, or I'm sorry, that's the y-intercept, that's the y-intercept. So that's the value when x is 0. So when x is 0, the drop height. When the drop height is 0, the flight time was negative 0.03761, which makes no sense. Most of the time, the y-intercept makes no sense in the context. But that's how you just need to kind of logical deduce that. Okay? The y-intercept. Well, the y-intercept is when x is 0. Well, when x is 0, that must mean the drop height was 0. That's like the initial starting point. The drop height is 0, therefore the flight time was negative, which makes no sense. But we know that sometimes those don't make any sense. Okay? Now they want me to estimate beta. Estimate beta. So I'm going to estimate beta. Well, that's going to be my slope. That comes from that one. Okay? That comes from that one. So we're going to estimate that value. Again, we need to know this stuff, but we should know this already from chapter 4. I know that was forever ago, so you probably don't remember it. That's why we go over it now. And the slope, if you remember, is always rise over run. It's always rise over run. Well, rise is your y. Your run is your x. Your rise is your y. Your run is your x. We know that. So I'm going up 0.00574 or 24, whatever. I'm going up. So when the flight time goes up by this, for every 1, I think it's centimeter, inch, my flight time exceeds or goes up 0.00571 seconds for every inch, because this number's over 1. The slope is 0.05724 over 1. So this is positive. It goes up for every 1 inch. And again, you just kind of logically deduce that from looking at the question. Talk to me, Harshith.
But is it the thing in centimeters?
Yeah, that's what I thought I saw too. This says inches for some reason. Where'd you see centimeters at?
Like in the actual computer now.
Oh yeah, that's what I thought. So that'd probably be me copy and paste something. What's the estimate for sigma? Interpret this value. I'm not too worried about that. Give the standard error of the slope, which is this one right here. There's the standard error of the slope. This all goes with slope. Okay. All right. So if you have to, I'm posting this slides. I think I already did, but here's A, here's B, here's S. That's that 0.16. That's this. We talked about that in chapter 4. Okay, that's the standard deviation of the residuals. That's the actual flight times, typically vary by about the line. And then there's the slope, or the standard error of the slope. Okay. I'm not too concerned that you can interpret this one. This one you should already know how to interpret. It won't be on this test. You should know how to interpret this one. It won't be on this test. You should know how to interpret this one. It won't be on this test. You need to know how to find A, B. You don't need to know how to find that. You need to know how to find that for this test. For the AP test, you need to know how to find this, 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 and this. But this is not in this chapter. Okay? The values the interpretations won't be in this chapter. The interpretations will not be in this chapter, but you need to know this interpretation. You need to know this interpretation. You need to know this interpretation, and I think you can get by without knowing this interpretation. Okay, any questions? Okay, confidence intervals for slope. Confidence intervals for slope. Again, slope. Everything's going to be about the slope. It's not going to be the y-intercepts. Everything's going to be about the slopes, not the y-intercepts. We know that this is already our formula. You have to turn these into variables. Well, the statistic is going to be B. Your statistic is going to be B. Plus or minus. I mentioned this already. Your critical value is going to be a T critical value. And then the standard deviation of the statistic is the exact same thing as the standard error of the statistic, which is nothing more than that. That's what it is, and that's what they're going to give you. They're going to give you those things because you're going to have to get it. You're going to have to get it from that computerized printout. You're going to get this from that computerized printout. Well, they give you this, and they give you this. They do not give you this. Wait a second, they gave me T. No, they didn't give you this T. They didn't give you that T. They gave you this T. Those are two different ones, right? This is not the critical value. This is the critical value. It's not the test statistic. Those are not the same values. Okay? So here it is right here. And then here's also what you need to know. This is like the biggest thing. I can almost guarantee you that that question somewhere on the AP test will be there. You need to know that the degrees of freedom is n minus 2. You need to know that the degrees of freedom is n minus 2. Okay? T star is the critical value for the T distributions, and n minus 2. It's because we have two variables. We have we have A and B. So because we have two variables, they are going to do n minus 2 for the degrees of freedom. That is, I have not seen an AP test that did not have that. I've not seen a practice test that didn't have something with that on there. I have not seen anything that didn't have the degrees of freedom being n minus 2. Okay? But like I said, rest of the stuff they're going to give you. So you got to know how to get the statistic, which you already know how to do. Now you know how to find this, which is right there, and that you already know how to find. I just got to remind you how to do it. Okay, you know how to find that from chapter 10. Just got to remind you. Okay. Caution: the T value that's given, guys, is not the critical value. That is the test statistic. That is the test statistic. These are different T's, and that's why they put the star there, right? When it's your statistic plus or minus that T star, that is not the same thing as the T is equal to the statistic minus the parameter over the standard deviation of the statistic. Those are different T's. This one you're finding, this one you're getting from the confidence level. Sometimes I got to make sure we understand that. Okay, because it's about this time where we start throwing all this stuff together and we're starting to get a little confused about that. Those are not the same. This comes from the confidence level. This comes from doing all this work here. Those are completely different numbers. This one you're turning into a p-value. This one you're not turning into a p-value. Truthfully, you already know the p-value for this one because it's like 95 or 90 or 99. So it's not, they're not the same. So the T that they give you in this computerized printout, that is not the T critical value. That is not the T critical value. That's the test statistic. Okay, please remember that. All right. Look, watch. Everyone knows that cars and trucks lose value the more they are driven. Can we predict the price of a used F-150? We did this example in chapter 4. If we know how many miles is on odometer, a simple random sample of 16 used F-150 Super Crew Cab 4x4s were selected among those listed for sale on autotrader.com. So here's all 16 of those. 1, 2, 3, 4, 5, 6, 7, 8 times 2. There's 16 of them. Good enough with all that stuff? Beautiful, beautiful. Look, it looks linear. Look, they look somewhat normal. Not really, but we're not going to deviate from it. And now the scatter plot, or sorry, the residual plot looks good and scattered, equidistance. We're going to go ahead and do this. Again, if I did one of these, I would say assume the conditions are met. All the ones on AP I've ever said, assume the conditions have been met. Here is what you need to have from it. Here's what we need from it. Okay? I guess I cut the question out. So they're going to say find a 90% confidence interval. Find the 90% confidence interval for the price of it, for the slope. They're going to say for the slope, not for the price. For the slope. So there's my estimator. Negative 0.16. It's going down, right? It's negative slope. The price is going down as the miles go up. Okay, so there's that value. I got to find the T critical value for 90%. And so that's where you have to use inverse T, or you have to use Coach Mayer program. And if you remember Coach Mayer program, it says something like n-1 for T's and n-2 for slopes for the DF. If you don't have Coach Mayer program, you got to do inverse T, but please, 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 you don't do inverse T of 0.9, right? because 0.9 doesn't find the critical value for the middle 90%. 0.9 is going to leave you short because it goes all the way out. So you have to find half a 9, or sorry, what's left over is 10. So you have to do 0.05 if you're going to do inverse T. 0.05 for inverse T. If you use Coach Mayer program, you can either use 90 or you can use 0.9. Okay? And it's going to give you that T star value, the critical value. And then we're going to multiply it by the standard error of that slope. It's a pretty easy problem once you just realize all you got to have out of it. You don't have to do really any work. You just have to know how to get the information from that table. We're not using the y-intercept. We're not using S or R squared adjusted. In fact, you can mark off R squared adjusted for everything because you'll never use that. I don't need this critical value and I don't need the p-value because it didn't ask me for the test statistic and it didn't ask me to find convincing evidence. It asked me to find the construct and interpret the interval. Any question about that? That's what you need to know. You need to know how to get the slope, how to get that standard error of the slope, and you need to know how to find that T critical value. And that T critical value is not negative 5.26. That T critical value you're going to have to get from doing inverse T or Coach Mayer program. Critical value. So there's the T star value, 1.76. It's a little bit different than 1.96 or 1.645. 90% is 1.645 for Z's. For T's, it depends on what the DF was. DF was 14 because there were 16 trucks. 16 minus 2 is 14. So there's the estimate, there's that critical value, and there's that standard error, right? And so you can leave it like this, guys. You can leave it like this if you don't want to do the mathematics. They will count it right if that's your interval. This is the true interval. And then conclude, we are 90% confident that the interval from here to here captures the true slope. That's what we captured, the true slope of the population regression line relating price to miles driven for used Ford F-150 Super Crew cabs. Again, I'm probably not going to ask you that part of it. If you can get this part right here, you're going to be fine. You're going to be fine. If you can find this right here, that's probably a multiple choice question on my test. Finding the T critical value for slopes. Because you got to know the degrees of freedom is 2. And you got to know to subtract that half if you're doing inverse T. Y'all okay with that? Question about that? Question about that? That's AP testable. That's my testable. This part right here. From this. From this. Not the conditions. Not the conditions. They don't care about the conditions. But they've always said conditions have been met. So I'm going to assume they have been met. Homework, you're going to have to worry about the conditions a little bit. Okay? Your calculator will do these, but I don't think you'll ever need it. AP does not want you spending time punching this up in your calculator. They don't. If you start having to punch a bunch of stuff in your calculator, you're doing something wrong. I'm just telling you, you're doing something wrong. Because at no point will AP want you to punch a bunch of stuff in your calculator because it tests nothing about your knowledge. It tests nothing about your knowledge. But it will do it. So if you punch all these into your X's or L1s and you punch all these in your L2s, you'll have 16 L1s and you'll have 16 L2s. And then you can go to Lin Reg T test. It's down at the bottom almost. Why would T int? Sorry, I said test. Int. 0.9. Boom. There it's going to give you the left bound. It's going to give you the right bound. It's going to give you what the slope was. It's going to give you the DF. It's going to give you the standard deviation. But that's everything that the table gave you. And the table, that printout. That's everything that the printout gave you. When you see a list of data values on an exam question, wait a moment before typing it all into your calculator. Read the question first. Often information is provided that makes it unnecessary for you to enter the data at all. This can save you valuable time. Okay, now let's talk about the test real quickly. And this one you can somewhat already understand it, right? You know that the standardized test statistic is equal to the statistic minus the parameter over the standard deviation. Well, in our particular case, the test statistic is going to be T. And the statistic is going to be B. And the parameter is going to be whatever Ho is. Most of the time it's beta. Most of the time it's beta, but whatever our Ho is. And then this is going to be SE sub B, which again, same thing, they're going to give you all this stuff. Most of the time, they're going to give you this. Most of the time, that chart's going to give you that value. Sometimes it doesn't. Sometimes it doesn't. But if it doesn't, it's got to give you this, and you got to know what this is, and it's going to give you this so we can find that without a whole lot of mathematics. Okay, so here that is. Again, T, B, hypothesized slope. What do we think the slope is? Most of the time, we think the slope is 0. Listen to me. Most of the time, we think the slope is 0 because we think that there's no relationship. We think that there's no relationships. We might think that there's a positive relationship. We might think there's a negative relationship, but most of the time, that's what we're trying to prove. That's normally the ha. So most of the time, we think it's 0, and if we think there's a positive relationship, then ha is greater than 0. If we think there's a negative relationship, then we think it's negative, less than 0. Again, your DF is n minus 2. Your DF is n minus 2. So when you're doing TCDF, make sure your degrees of freedom is n minus 2, not n minus 1, because I promise you that will be one of your answers on the multiple choice. Real quick, infants who cry easily may be more stimulated than others. This may be a sign of higher IQ. Child development researchers explored the relationship between crying of infants and 4 to 10 years old. IQ test, a snap of rubber band, made them cry. That's so mean. Later, they measured the child's IQ after 3 years. Standard IQ test, the table shows 38 infants. Cry count, IQ. Cry count, IQ. I guess there's 38 of those guys. Yo. Probably not going to have to put that in my calculator. Oh, I don't. Look, that looks linear somewhat. I'm not too sure how great it is. It's not. R squared is 20%. Not great. Residual plot. Ooh, that's iffy. We're starting close. We're expanding, but there's the residuals. Again, you're going to have to know that for your homework, and that's it. I'm not going to ask you that on test. Here's this important stuff. I don't care about the constants. Here I care about the cry count. Here's my slope. Here is the standard error. There's the T critical value, and there's the P value. I don't think I'm going to have to do much at all. Do these data provide convincing evidence at 0.05 of a positive linear relationship? Oh, beta equals 0. Beta, don't put B, because B is the sample. It always alludes to the population. Ha, positive relationship. And then you have to tell me what B is. B is the true slope of cry count versus IQ, or IQ versus cry count, or whatever, however you want to say it. Okay, so we need to know that part of it. We kind of do, but we need to know that, all right? Now, here's another little trick that they're going to give you, though. Okay, here's another little trick. That P that you give you is always from a two-tailed test. That P that they give you is always from a two-tailed test. So that means it's been doubled. That P has been doubled, and if I'm not testing doubled, then I need to cut it in half. I need to cut it in half. And that's why they had to cut that value in half. That's still the T critical value, but that P value, note, the P value is for a two-sided test. There is evidence for Ha, but we cut the p-value in half for a one-sided test. So just make sure you remember that, okay? This is always the p-value for two-tailed test. So if we're only doing one-tailed test, we need to cut that in half. What else do I got? Oh, because P is less than alpha, or you want to reject, you could have still got that wrong and still rejected it. There is convincing evidence of a positive linear relationship. And the reason why there's convincing evidence of a positive relationship is because we said that that's what my Ha was. Your calculator will do these also. Again, I don't think you'll ever need it. You'll go lin reg t test. You have to put your x values in L1, your y values in L2. Frequency is always 1. We're trying to prove it's greater than 0. Calculate. When you hit calculate, there's the t, there's the p. Notice that that's 0.02. If I want this one over here, it would be 0.04. There's your DF. DF is 36. You need to know that DF was 36 and because there were 38 points. There's A, there's B, there's S. That's everything that your that table gives you anyway. For homework, you'll need to know how to check the conditions, but that's it. Interpret the values of B sub 0, B sub 1, sigma, and SE sub B. You don't need to know that for the test. Construct and interpret a confidence interval from the slope of the population of a true regression line. That you'll need to know from a computerized printout. Perform a significance test. You'll have to know how to do that from a computerized printout. I'm going to give you a computerized printout. If I'd even give you one at all. Y'all okay with that? Good? They won't go anymore. What time is it? 8:08. I don't know if it posted. Yeah, I think so. I think it posted.